Chapter 1, AP Chemistry. You must have your guided notes available as you complete this video. Those notes are due on the first day of school. Okay, the first thing we have to talk about is the law of conservation of mass. Now, you've all heard about it from honors. Matter cannot be created or destroyed, and it has to be conserved. Basically what that means is during a chemical reaction, bonds are broken and then new ones are created. But the amount of matter that is present in both the reactants and the products has to be equal. You're going to see this a lot in AP Chemistry with diagrams. So if you look at the left diagram, okay, you see two open circles, two white open circles, right? You see one here, hold on a sec, one here, and you see one here. Well, you have to have exactly that many in the other photo. Same thing with all the other ones. You have two grays and two grays, and then you have 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6 reds. You guys will see that in AP Chemistry, they will give you the products drawn correctly, but you have to make sure the law of conservation of mass is still being obeyed. You guys also are more than well aware about the three states of matter: solids, gases, and liquids. Just make sure you know that solids are rigid, they have a fixed shape and volume, they are moving, the atoms are vibrating back and forth, no matter ceases to not move. They all have some form of energy. Liquids are basically incompressible. You can't force them into a smaller amount of space. They have a fixed volume, but their shape is not fixed, so they take the shape of their container. And gases are easily compressed, and they do not have a fixed shape or volume. The difference between physical changes and chemical changes: physical change is just changing the form of the matter, but not its identity. So like when water boils, it's still water. It's just now water vapor. So all changes in state, boiling, melting, freezing, are all physical changes in addition to things like cutting, bending, whatever. A chemical change is when there's one or more kinds of matter is transformed into a new kind of matter or several kinds of matter. There are 5 pieces of evidence that a chemical change has occurred. So these are things you would see in a lab that would tell you that a chemical change occurred. The first one is a change in color. The second one is a precipitate forming, which is a solid. The third one is a production of a gas, which you would know that if you saw bubbles or steam or things that would signify to you that a gas had formed, or you smelt an odor. The fourth one is energy changes. You might feel some hot or feel some cold, see some sparks of light, or hear a popping sound. All of that would indicate that you have a chemical change. And the last one, which is the worst one and the weakest one, is irreversibility. It sometimes works, it sometimes doesn't. So for example, you tear a piece of paper in half, you can't put it back together naturally without using tape. But just because you can't put it back together doesn't mean that tearing a piece of paper in half is a chemical change. It's still a physical change because it's still paper. So be careful with the last one because it's not always the best one to make your prediction on. You should have evidence from one of the other 4 to also help back you up. You're going to see a lot of diagrams in AP Chemistry, and we're going to get good at them quickly. The first one here shows you the before and the after. So what do you notice about the type of matter? Well, in the beginning, they're all purple spheres, and then in the end, they're all purple spheres. All that's happened is it looks like it's been bent. So is bending a physical or a chemical change? And of course, you should be saying to yourself, it's physical. The next one, the before and after. If you look, in the before photo, you have like these that looks like it could be like a methane, like a CH4. And then on the other side, there is no CH4. They've all been broken up. The bonds have been broken between the blacks and the whites, and they've been rearranged. This tells you that a chemical change has occurred because you now have a new form of matter. Next one. Looking at the beginning and looking at the after. These look like water molecules to me. 2 H's and an O. And if I look over here, I still have 2 H's and an O. All that happened is it looks like they spaced out more. I would say this is like an example of a liquid. This is an example of a gas. So what happened here was vaporization. And if vaporization occurred, then this is a what kind of change? You should be saying this is a physical change. Okay, in this one, we have two reactants. We have reactants in the top sphere and in the bottom one. So here it looks like it's water. In the top one, I'm not really sure what that is, but it does look like when I go into the other picture, that compound is still intact, and so is the water. So all that happened was these two were mixed together. Nothing actually changed about the matter. So this is also a physical change. Now, the other topic you guys have to be good at is accuracy versus precision. Accuracy is how close a measurement is to its true value, or what it's supposed to be, and precision is how close the measurements are to each other. Reproducibility. Can you reproduce your measurement, good or bad? If you look in this first photo, this is not accurate or precise. To be accurate in a bullseye, you want to hit the center, and this is where you want to hit. And it's not hitting there, and all of these arrows are not all in the same location, so it's not precise either. The second one, they all look to be pretty clumped together, but they're not hitting the bullseye. Therefore, they are precise but not accurate. The last one, they're hitting the bullseye and they're all together. This is an example of how you can be accurate and precise. Sig figs. You guys have got to know your sig figs. Some teachers don't emphasize it in honors. I do. But you need to know your significant figures, and I will hammer you on significant figures. So the first thing to know is that the definition of significant figures are all the measured digits of a measurement and then one estimated digit. This also comes into play when you guys read equipment. We will go over this in class so that I can guide you, but you must be able to estimate a digit when reading glassware in lab. You also have to be able to correctly count the number of significant figures in a number. Now, depending on your teacher, you may have learned a bunch of rules about trailing zeros and captured zeros and all this other junk, but I only teach you one rule that you must know to be able to count the number of significant figures. The rule is called the Atlantic-Pacific rule. If you know where your Atlantic Ocean is and your Pacific Ocean, then you can do this rule. The Pacific Ocean is located on the coast of California. The P in Pacific will remind you that when you are in the presence, P, of a decimal, you start on the Pacific side of the number. The Atlantic, A in Atlantic, stands for absence of a decimal. When there's no decimal written in the number, you don't worry about, oh, well, there's an understood decimal. All I'm saying is, do you see a decimal or not? If there is no decimal, you start in the Atlantic side. So when you have to deal with a number, okay, like how many significant figures are in 1.6502, you can draw an imaginary box around the number, or if you really feel like it, draw a real box. I don't care. Remember that if the box represents the continental United States, the Pacific Ocean was on the left and the Atlantic Ocean was on the right. If you look at this number, do you see a decimal? Yes. So are you in the presence or the absence? Presence. You start on the P side, and then you have to start counting digits after you hit something other than 0. So what I mean is, if you're starting on the Pacific side, your goal is to go cross-country and get to the Atlantic side. You will start counting when you hit something other than 0, anything else but 0. And if you notice, the first thing we hit is a 1. I will start counting because 1 is not 0. That means I have 1, 2, 3, 4, 5 significant figures. So how many significant figures are in 15,020? Again, imaginary box. Are you in the presence or the absence of a decimal? Well, there is no decimal written on this number. You need to go cross-country. Start counting when you hit something other than 0. Well, the first thing I hit is a 0. That doesn't count. I start counting when I hit something other than 0, which is the 2. All these numbers count. Once you hit something other than 0, all the numbers that are left count. So that is 4 significant figures. You also have to be able to do calculations with your significant figures. The first type of calculation is whenever you do addition and subtraction. When you do addition and subtraction, your answer has to be rounded to the least number of decimal places in the problem. So when you look at the question, Okay? You're going to decide how many decimal places are in each of the numbers and then round your answer to the one that has the least number of decimal places. Multiplication and division is a little different. You will round to the least number of significant figures instead of the least number of decimal places. So in number 1, the calculation in the leftmost box says 2.030 minus 1.870. If I plug it into my calculator says 0.16. I have to determine if that answer is correct that way or if I need to change it to abide by the rules of significant figures. Since I am subtracting in the first one, I need to do the least number of decimals because subtraction is the least number of decimals. In 2.030, there are 3 decimals. In 1.870, there are 3 decimals. Therefore, I must have 3 decimal places in my answer, and 0.16 is only 2. So I have to manually add a 0 to abide by the rules of significant figures. The second one is multiplication. I will do sig figs. Applying the Atlantic Pacific rule to 3.24, I am starting in the presence of a decimal and moving this way. That means I have 3 significant figures. In the second one, I'm also in the presence of a decimal. Once I hit that 7, all numbers count, so I have 2 significant figures. Out of 3 and 2, 2 is the least. So when my calculator says 22.68, I know that's not the answer because that has 4 significant figures and I'm only allowed 2. To keep 2, I'm going to keep the 2 and the 2 and chop it off. The 6, however, tells me to round up, so my answer becomes 23. The third one, 710, has only 2 significant figures because in the absence of a decimal, I go from the right to the left. That first 0 I hit does not count, so it's 2 significant figures. 3.0 also has 2 significant figures because I start from the Pacific side of the number because I'm in the presence of a decimal, and I head to the right, so I have 2 sig figs. If I have 2 and 2, then this answer must have 2. This is where students struggle. They know they want to keep the 2 and the 3, so a lot of them tell me it's 24 because the 6 next to it tells them to round up. Newsflash, 24 is nowhere near 236.66666667. So you must add a 0 as a placeholder, and I still have 2 sig figs because if I'm in the absence of a decimal, I start on the right, I move to the left, and I still have 2 sig figs. So zeros can be placeholders. In the next one, it is addition. I have 1 decimal here, 2 decimals here. That means I can only have 1 in my answer. My answer will become 1821.6. The last one is now multiplication. 5 sig figs, 3 sig figs. That means I can only have 3. I'm going to keep the 5, the 8, the 7, chop it off. It's not 587. Remember, add that 0 to hold the value of the number. You also have to be able to do metric conversions. I expect you to know the phrase King Henry died by drinking chocolate milk, and I expect you to know what each of those words means. King stands for kilo, Henry stands for hecta, died is the capital D, which is deca, by is the base unit, which could be the liter, the gram, or the meter. The little d for drinking is deci, centi is chocolate, and then milli is representative of milk. The bigger units are on the left, towards the kilo side, and the smaller units are towards the right, which is the milli side. If you want to know how many decimeters are equal to 1, let's say, kilometer, this is how you do it. You put a 1 next to the bigger unit, okay? So let's say that. We were going to do kilometers are equal to decimeters, okay? What's bigger? A kilo here or a deci here. Clearly, kilo's bigger. So you put a 1 next to the bigger unit and then count how many movements or transitions it takes you to get to the other unit. So to get from deci to kili, I have to go 1, I have to go 1, 2, 3, 4 transitions. That's the number of zeros you put after a 1 on the other unit. So a 1 followed by 1, 2, 3, 4 zeros means there are 10,000 decimeters in 1 kilometer. So you need to be able to do this. So I gave you a bunch of examples here. I will do 2 with you. You are responsible for doing the other 2 in your notes, and I will check that you did so when you come back to class. So centi or hecta, which one's bigger, hecta or centi? Clearly hecta. Put the 1 there, and then count the number of transitions. Seems to be 4, so that would be 10,000 centigrams are equal to 1 hectogram. Let me erase this for the next one. Meters, millimeters. Okay, a meter, remember, is not the M. The meter is the base unit. Meter, millimeter. Which one's bigger? The meter. How many transitions? 3. That means 3 zeros after 1. That's 1,000 millimeters is equal to 1 meter. So you go ahead. You figure out, by pausing the video if you need to, the last 2 conversions on your paper. You also have to know how to calculate density. Density is defined as mass over volume. You also need to know that it's a conversion, and you're going to be using it in your conversions, your grids, your dimensional analysis, whatever you call it, for the rest of the year. Okay, it allows you to convert between any unit of mass, whether it's the gram, kilogram, milligram, and volume, liter, milliliter, centimeter cubed, okay? The other thing you need to know is what is the density of water, and I'm telling you now, you must know this unit by heart. You must know that the density of water is 1 gram per 1 milliliter. So what's the density of water in hectograms per liter? Well, if I ask you a question such as that, it is a dimensional analysis question. You're going to convert. Notice, in the end, I want hectograms on the top and liters on the bottom. As of right now, I have grams on the top and milliliters on the bottom. It's a double conversion. I got to convert grams to hectograms, and I got to convert milliliters to liters. Where you start does not matter. Most students will start with the top. So if I want to get rid of gram, gram has to go on the bottom, and what I want is hectogram. Using King Henry died by drinking chocolate milk. I know that the gram is here, and I know that hectograms are here. Hecta is bigger, it gets the 1. 2 conversions means there's 100 grams in a hectogram. The grams have canceled out. Now, if I stopped, I would have hectograms over milliliters, and I want hectograms over liters. So to get rid of the milliliter, I'll put milliliter on the top, because it's currently on the bottom, and liter on the bottom. Out of liter or milliliter, which one's bigger? The liter, so it gets the 1. Liters are in the base unit. Milliliters are here. It takes 1, 2, 3 conversions. That's 1,000. The milliliter and the milliliter cancels, and you're left with hectograms per liter. Plug it into your calculator and solve, and you're going to just get plain old 10. But 10 is not correct. If you look at the original number had 2 significant figures. Whenever you do a conversion, you must keep the same number of significant figures as the original number. If that has 2, this needs 2. So I add a decimal after it to give it 2 sig figs. Last thing from chapter 1. You should not have found any of this difficult. If it is, you guys are in trouble. The last thing you need to remember how to do is how to convert temp. To convert between Celsius and Kelvin, you need to know that you add 273 to the degree C to equal the Kelvin. Make sure you pay attention. You're adding, so when you do this, it's the least number of decimals, and you're adding 273 every time. That means that 273 is a constant and does not count when you consider the sig figs in your answer. So if I want to convert 17 degrees Celsius to Kelvin, it's a little sketchy, but all you have to do is add 273 and you get 290. But that is not correct. Because this has no decimals, you're saying that all of these numbers have to be significant before the decimal. The only way to make all of them significant is to actually put a decimal place after the 290. Otherwise, if you just did it like this, only the 9 and the 2 are significant. So whenever you're doing temp conversions, If you get a whole number that ends in a 0, I suggest you put a decimal point after it. If it had been like the next one, 273 plus 17.0, this 17 has one decimal. That means I must keep one decimal, so my answer is 290.0 Kelvin. Alright, that's the end of this video. See you soon.